Ancient doctors often got the diagnosis right without knowing why they were right. Modern AI often gets the diagnosis right without knowing why it's right either. One had no germ theory. The other has a black box problem nobody can fully explain. Two totally different eras run into the exact same wall. Accuracy without understanding. Stick around, because how each one dealt with that gap tells you something important about how humans actually solve hard problems. Imagine someone hands you a sealed metal box. Every few minutes, it makes a different sound. A click, a hiss, a low rattle. Your job is to figure out what's wrong inside it. You can't open it. You can't look inside. All you have is what it shows you on the outside. This is, essentially, the problem every doctor in human history has faced. The human body doesn't open itself up for inspection. For most of history, physicians couldn't see a tumor, a blocked artery, or an infection. They could only observe symptoms: fever, swelling, pain, color, breath, and try to work backward to a cause they couldn't see. This mattered enormously in the ancient world because getting it wrong meant death, often quickly. But it still matters today. Even with MRIs, blood panels, and genetic testing, one large study published in the journal BMJ Quality and Safety estimated that roughly 12 million American adults experience a diagnostic error every year. The problem was never a lack of intelligence. It was structural. Any diagnostic system, ancient or modern, has to do three things at once: gather the right signals, find a reliable pattern linking those signals to a cause, and do this consistently, without ever directly seeing the thing it's diagnosing. That's why, thousands of years apart, two completely unconnected civilizations built the same kind of solution. Around 1600 BCE, someone in Egypt copied out a medical text now known as the Edwin Smith Papyrus. Scholars believe it may have drawn on material even older than that. What makes it remarkable isn't just its age, it's its structure. Case after case follows the exact same format. First, an examination, what the physician sees, feels, and observes. Then a verdict, a judgment on whether the patient can be treated, might be treated, or cannot be treated. Then, if possible, a treatment. Examine. Compare to what's known. Predict the outcome. Act. There's no theory of anatomy behind it. No concept of blood circulation or nerve function the way we understand them now. The Egyptian physician didn't need to know why a certain injury tended to end badly. He only needed to know that, in past cases, this pattern of symptoms had reliably predicted that outcome. A few centuries later, in Mesopotamia, a physician named Ishagil-Kinapli compiled something even more systematic: the Diagnostic Handbook, dated to around the 11th century BCE. According to Assyriologist Joan Scurlock, who has translated much of this material, the handbook organized ailments by symptom clusters, walking through the body region by region and matching observed signs to likely prognosis. Neither system required understanding germs, viruses, or blocked arteries. What they required was documentation. Someone had to observe enough cases, write them down accurately, and organize them so that a different physician, reading the same text somewhere else, could reach a similar conclusion from similar symptoms. This is worth sitting with for a moment. These texts weren't just records of individual cases. They were something closer to a manual, a set of rules, meant to be followed by someone who wasn't the original author. That's a very specific kind of achievement. It turns one person's experience into something that can be reused by strangers indefinitely, without them needing to rediscover it themselves. In other words, ancient physicians weren't guessing. They were running a formalized, rules-based system. Gather the signal, compare it to a known pattern, predict the result. It's an algorithm written by hand, on papyrus and clay, centuries before the word algorithm existed. And that exact structure, observe, compare, predict, didn't disappear when microscopes and anesthesia arrived. It just found a new home. Not in a physician's memory this time, but in a machine. In 2018, researchers from DeepMind and Moorfields Eye Hospital in London published a study in the journal Nature Medicine. They had built an AI system that could examine retinal scans and detect signs of over 50 eye diseases, matching the accuracy of expert ophthalmologists. A year earlier, a separate team at Stanford published a study in Nature showing a deep learning model that could classify skin cancer from images, again performing on par with board-certified dermatologists. Here's how these systems actually work, stripped down to the basics. You feed a neural network a huge number of labeled examples, thousands or millions of scans, each one tagged with the correct diagnosis by a human expert. The system doesn't get told what a tumor looks like or what a diseased retina is supposed to look like biologically. It's simply shown enough examples, correct and incorrect, until it starts recognizing statistical patterns that correlate with the right answer. Notice what hasn't changed since the Edwin Smith papyrus. There's still an examination, the scan or image. There's still a comparison, matching new input against a vast library of prior cases. And there's still a prediction, an output that says, this pattern most closely resembles disease, or it doesn't. What's different is the scale. A Babylonian physician might draw on a working knowledge of a few hundred cases across a career. A modern diagnostic model can be trained on millions of labeled images, drawing on statistical patterns no human could hold in memory at once. But there's a catch, and it's an important one. These systems often can't fully explain their own reasoning. A neural network might correctly flag a scan as cancerous, but the exact combination of pixel patterns that led to that conclusion can be nearly impossible to trace, even for the engineers who built it. In machine learning, this is known as the black box problem, and it's been widely documented, including in the Stanford skin cancer study itself, where researchers noted the difficulty of fully interpreting the model's internal decision process. That should sound familiar. The Egyptian physician also couldn't explain, in any modern biological sense, why a certain wound pattern predicted death. He just knew, from precedent, that it usually did. Different centuries, different tools, same fundamental trait, real, working accuracy, without full understanding of the mechanism behind it. Strip away the papyrus and strip away the silicon, and Diagnosis turns out to be made of the same four parts, no matter the century. First, signal collection, the raw information gathered from the patient, whether that's a physician's hands-on examination or a digital scan. Second, a pattern library, the accumulated set of prior cases available for comparison, whether stored on a clay tablet or inside a trained neural network. Third, a matching step, the process of comparing the new case to that library. And fourth, an output, a prediction or verdict that leads to some kind of action. Every diagnostic system in history, from a Babylonian scribe to a modern algorithm, is really just a different way of filling in those four slots. Once you see that shared skeleton, the similarities stop looking like coincidence and start looking like convergence. Both systems reach real, usable accuracy without complete causal understanding. The Babylonian Handbook worked without germ theory. The Stanford model works without fully explaining its own internal logic. Both rely on accumulated precedent rather than a single flash of insight. A large set of prior cases, not one person's intuition, is what makes the prediction reliable. Both require documentation to scale beyond a single practitioner. A Babylonian physician had to write the handbook down so other physicians, in other cities, could use it. An AI model has to be trained and distributed so hospitals elsewhere can use it too. And both share the same core vulnerability: bad input in, bad output out. A poorly observed symptom in an ancient case record could corrupt future diagnoses, just as biased or incomplete training data can corrupt a modern model's predictions, a risk documented in multiple studies on algorithmic bias in medical AI, including research published in Science in 2019 showing racial bias in a widely used healthcare risk prediction algorithm. But the comparison isn't perfect, and forcing it to be would miss what's actually interesting. The differences are just as revealing as the similarities. Scale is one. A career physician in ancient Mesopotamia might draw on a few hundred cases. A modern model can draw on millions. Correction speed is another. Ancient diagnostic texts were updated slowly, sometimes across generations, as physicians observed new outcomes and revised the handbook. A modern AI model can be retrained in days, which sounds like pure improvement, but it also means errors and biases can scale just as fast as accuracy does. Transparency is a third difference, and arguably the sharpest one. The Edwin Smith papyrus, whatever its flaws, is at least human-readable. Another physician can follow its logic, case by case. A deep neural network often can't be read that way at all, even by the people who built it. And finally, the stakes of failure have changed shape. A flawed prognosis in ancient Egypt affected one patient. A flawed pattern embedded in a widely deployed AI model can affect a population. All of this points to something bigger than medicine. Whenever a system can't directly observe what's happening inside something, a body, an economy, a machine, it tends to fall back on the same basic move: codify patterns from precedent, and use those patterns to predict outcomes, even without fully understanding the cause. This isn't unique to medicine. It's the same underlying shape found in legal systems built on case precedent, in weather forecasting models built on historical data, and in credit scoring systems built on past repayment patterns. Diagnosis just happens to be the oldest, clearest example of it, which raises a genuinely uncomfortable question. If accuracy without full understanding was good enough to build ancient medicine and good enough to build modern AI, does the why behind a correct answer actually matter? The historical record suggests a specific answer. It's not that black box accuracy is inherently untrustworthy. It's that trust in a black box has always required something else running alongside it, a mechanism for catching and correcting errors over time. Babylonian and Egyptian medicine survived for centuries, not because their case libraries were flawless, but because physicians kept observing outcomes and revising the texts when the predictions failed. The modern equivalent is the growing field of AI interpretability research, along with clinical auditing and testing standards designed to catch when a model's pattern matching goes wrong. The tools change completely. The core mechanism, pattern matching without full understanding, kept honest by ongoing correction, has stayed remarkably consistent for 3,500 years. So here's the question this really leaves us with. We've spent thousands of years building systems, clay tablets, papyrus scrolls, neural networks, that can be right without being understood. Babylonian scribes trusted their handbooks. We're increasingly trusting an algorithm's verdict on a mammogram or an MRI. So, where's your own line? How much accuracy would it take for you to trust a diagnosis you can't fully explain? Drop your answer below. I read every one, and I'll pin the most interesting take.